So I think I wanted us to just go through the final part of the notes. I think I started sharing something. Share. So I just wanted us to clean up this together. Are you able to see the notes?
Yes.
Yeah, so I think we will just remind ourselves as we clean up this. So there's the introduction, what we said, this one, environmental chemistry, what it is. I think we could, environmental pollution, what it is and what are the areas, then the pollutants. Talked about the symbol parts per million. It's the concentration of 1 parts per million. You can express it in terms of 1 parts per billion or 1 parts per trillion. So it's just 1 over a million. The other one is 1 over 1,000 millions. A billion is 1,000 million, and then a trillion is a million million. And then we talked about the major pollutants. Remember, we said the oxides of nitrogen, they cause acid rain. They also take part in photochemical reactions where they also affect the concentration of ozone. We talked about sulfur also, acid rain, and then and we know the effect of the acid rain, hydrogen sulfur, the smell. Carbon monoxide, we say it is poisonous. Carbon dioxide, greenhouse or global warming. Remember we talked about those radiations not reaching the earth because of when you have a layer of these greenhouse gases, the radiations will strike the sun, but when they are reflected, they'll not escape back because they'll emit a blanket of these gases, which will cause global warming. And we talked about the effect of global warming. And then the halogens, we talked about the halogens. They play an important role we talked about depletion of ozone. Remember, we talked about the CFCs and so on and so forth. And then solid pollutants, we talked about the metals. I said for the metals, we need to know their sources, their effects, and what are the measures that we normally take with these ones. To remove the metal, we talked about phytoremediation, where you remove by planting crops which can absorb the metal. You can use chemical means. We talked about EDTA. They can do that. And then talked about photochemical reactions. Remember the 5 reactions of photochemical smog, where you have the nitrogen, ozone, oxygen, nitrogen dioxide, the PNA, the peroxyacetyl nitrate reaction. We need to know those reactions. Sometimes you can be asked to do those ones. And then there are also other solid waste that we need to know. Dust, herbicides, fungicides, pesticides, we talked about that. And we said for the pesticides, their effect, how do they affect the insects? We say they affect the production of an enzyme called acetylcholine, which is important in neuron transmission. So generally it affects the nervous system. And we said why they are poisonous is because they can also affect us. If we overuse them if we overuse them, then they can also affect us. So they can get the target and also get us. And that's why they are not very friendly. And we said for the pests, herbicides, the thing to remember here is some of them are not biodegradable. So we need one which is biodegradable, and not just biodegradable. Biodegradable means breaking down, but it should break down into forms which are friendly. It can break down to form metabolites which are also harmful than the parent material. So we need for it to be biodegradable so that it doesn't persist in the environment, but it should form products which are friendly. So we talked about biodegradability as being a major issue for these pesticides. Talk about bioaccumulation. When we talk bioaccumulation, we say it's taken in by the plants and then through the food chain, it's able now to reach the untargeted organisms. Okay, and then we have radioactive material causes cancer. So for the industrial waste, we talked about things like chromium, which are used in tanneries for coloring. And then we also have some microbial contaminants. You have heard about aflatoxins and so on. When you don't store maize properly, they normally get infected by this, and some of these things are carcinogenic. So I think, so the important thing, talked about degradable, biodegradability, able to break down into friendly products. Heavy metals, they are not biodegradable. So they accumulate to a larger amount, and then they become biomagnified. They accumulate. Biomagnified means they keep on accumulating slowly, and then they accumulate where they are stored in the body tissues and food chains. And when we have that, then they become poisonous. And we say they can react with other compounds in the environment, even to produce more harmful products. The biodegradable ones are good, like the sewage waste. Those ones can break down. Yeah, I think you have had, you saw, I think there are people who are able now to even produce fuel from human waste. What they do is that they treat it to remove the microorganisms, and then heat it to form carbon, and then they're able even to use it as charcoal. I think there's a farm in Nakuru which is doing this, generating charcoal from human waste. So I think this is what we are talking about. They can break down and form other products which are friendly. The DTTA, some of these chemicals have said, okay, the organic ones, they don't break down at all, like DDT, but there are some which break down and form friendly products. So we say the difference between contaminants and pollutant, we should be able to know. We say a pollutant is detrimental. It has negative effects. A contaminant may not. It's just there in large amount and may not have any effect. So contaminants, generally, they are not classified as pollutants. Like, for example, we can have cases of a good example of a contaminant is peppers. When you have people, the peppers that we normally use to write, we know that they are not supposed to be littered anywhere because they don't cause any direct harm to human being. But we know when they accumulate, they might cause what we call blockages of drainage. And when this when the drainage are broken, then you're likely to have these waterborne diseases cases coming up. So as when you look at the newspapers, we cannot look at them as pollutants. They're just contaminants. When you have them not properly disposed, then this is the effect that they may cause. And then we talked about, we're just trying to brush through as we wait for our friends to see if they'll join us. We talked about a threshold value, a limit. We said for these chemicals, the amount that somebody should be exposed to must be controlled. Otherwise, if it passes that amount, then they become threshold, they become harmful. So when you say about threshold limit value, TLV, it is the permissible level of the toxic pollutant in the atmosphere to which a human industrial worker gets exposed during 8 hours, which we say is the normal working day. So if it surpasses that amount, then it becomes an issue. And then, so for this, where we get these values, so these values can be gotten from, there are organizations which have set the standards. One of them is WHO, World Health Organization. It has set the levels of these metals or pollutants to which somebody can be exposed. And then in Kenya, we have KEBS. KEBS, I think, has also come up with some values, especially in food stuff. That's why they do testing of this food stuff to ensure that we don't have these problems. So what normally happens is if they are not checked, then we shall have issues. You remember last time, I think it was about 3 months ago, where they withdrew some cooking oils from the market because they had excess iron. So you can see that's one of the role of KEBS. When they tested a few, they discovered the amount of iron was in excess. So I think that's what we mean by that. And then we talked about a receptor. So a receptor for this case means anything that can be affected by the pollutant. So an inspector is anything. It could be us, it could be the animals that we keep, cows, chicken, and so on and so forth. And then the sink, this is where these pollutants can settle, can be retained. It can be retained, not necessarily in the human body. We say they can go into water, they can go in the soil, they can also go into buildings. So a sink is a medium which is able to retain and interact with this pollutant for much longer time. So for us, we cannot be a sink, because if it's accumulate for some time, then we'll get affected, and maybe the effect would be death. So we said one example of a sink is the walls. The walls, the walls of buildings which are made of cement. Cement contains calcium carbonate, what we call limestone. Now, when you have acid rain, which falls in form of sulfuric acid, it can react with the wall to form calcium sulfate plus carbon dioxide plus water. So we are able to get this. So the wall, therefore, will serve as a sink, because it's now acting as a media through which this pollutant can be stored for a much longer time. So I think that's what we said there. Then we talked about the pathways. How do we get these things? Can get them, like, for example, lead as a metal. We said previously, they used to sell what we call leaded petrol. Leaded petrol was being sold because lead used to assist in what we call anti-knocking. Engines were knocking, so they used to add this tetraethyl lead in petrol to prevent what we call engine knocking. So this lead at high temperature, when the engine is functioning, it could break down. The compound could break down and form some compounds like lead chloride, lead bromide, which in turn would get into the food chain. And when this one gets into the food chain of the soil, then they were able to get into our bodies. And then we have nitrogen dioxide. Again, we said the fossil fuel contains some nitrogen dioxide because it's actually formed from fossil, dead living, formed from living organisms. Once they die, they decompose and generate this kind of fuel. So because they are made up of proteins, they contain also nitrogen. So when in the process of heating this, we can also release nitrogen dioxide, which we said is an example of a gas that forms acid rain. We said nitrogen dioxide, when it reacts with water, it gives you nitrous acid. And we also saw that it plays an important role in photochemical reaction. The formation of the fog, we said the brownish color of the atmosphere that we see is because of the nitrogen dioxide. Carbon monoxide, this one we form when the fuel does not burn well. When the fuel does not burn to completion, then we get carbon monoxide. And we say the danger of this is that it competes with the oxygen for hemoglobin. So ukikuwa na carbon monoxide, it takes the site which is supposed to be occupied by oxygen. The effect is oxygen cannot be transported in the body. And if we lack oxygen, of course, we know oxygen is everything, respiration, then this causes death. Then for speciation, this talks about different forms of metals. These metals, they exist in different forms. Like, for example, if you talk about aluminium, or for example, lead, you can get lead in different forms. You can have lead in form of lead nitrate or lead ions. You can have lead in form of lead carbonate. You can have lead in form of maybe PB, brackets OH4 negative, a complex of lead, where you have the lead hydroxide plus 2 hydroxides to form the complex. So when you have that, it becomes the form, so it takes different forms. And why are we interested with the form, or what we call speciation? Because the speciation will determine the chemistry. The speciation will determine whether these ions will move. The speciation will determine whether they'll be soluble in water, will affect solubility, mobility, and solubility and mobility will also determine if they'll be able to get into our bodies. So if they are more soluble, then it means they are more toxic because they can easily get into water. Plants can pick them up, and then eventually when we eat these plants, then the same can get into our bodies. So I think we need to know speciation talks about the form or the species by which an organic compound exists in the atmosphere. So we are just revisiting because I think when we are doing this, we might have rushed very fast. So we just want to catch up a bit. And then there are parameters that we use to check whether water is clean or not. So we talk about physical-chemical parameters of water. Physical-chemical parameters. They'll tell us whether that water is clean or not. Now, one of the ways of measuring the cleanness of the water, you can measure what we call dissolved oxygen, how much oxygen has dissolved in the water. And this is important. We shall see that if you have less oxygen, then what it means is that you have too much microorganisms in that water, which is consuming the oxygen. And that will mean that it's not very good. So we have, for water to be of good quality, the concentration of dissolved oxygen is between 4 to 6 milligram per liter. That means for every liter of water, you must have between 4 and 6 milligrams of oxygen. So anything below or above this, then we say that this water is polluted. And we just use this to measure the amount of microorganisms in the soil. Okay, biochemical oxygen demand, BOD. So this one again is also a measure of the purity of water. So water, we have got what we call it physical chemical, meaning you're measuring the physical properties like pH, like temperature, but there are also chemical properties. So these are the chemical properties that we measure. Now for biochemical oxygen demand, this one is the amount of oxygen that is required by microorganisms to break down chemicals in the body. So these microorganisms need oxygen. So the amount of oxygen needed by this microorganism is what we call biochemical oxygen demand. And this is the oxygen that is the amount of oxygen that is needed by these microorganisms to break the chemicals. Normally they talk about in 5 days because they set a limit. Now again, this is also used as a quality to measure the amount of organic matter in water. So a good drinking water should have between 0.7 to 0.5 milligram per liter of what we call biochemical oxygen demand. So it's again an indicator of pollution, because the more oxygen you have to break this organic matter, then it means the more organic matter you have. And the more organic matter you have, then this means the less pure is the water. Then we have now the chemical oxygen demand. Again, this one is also a measure of the amount of oxygen in the water. So what we'll see from this that is, so this just measures the concentration of water. So this one is just a measure of the concentration of oxygen in water supply, and it just tells us how much oxygen will be present to oxidize chemicals in the water. So the biochemical oxygen demand is the amount of oxygen needed by microorganisms to cause decomposition. But the chemical oxygen demand is the amount of oxygen needed to oxidize these a chemical. So this one is also an indication of purity of water. So the higher value means we have more substance to be oxidized, and that tells us that the water may not be pure. We talked about eutrophication. We are just trying to catch up. So this one we said when you have things like sulfate, when you have things like phosphate, these nutrients, sulfate, phosphate, nitrates, if you have excess of this coming maybe from our homes, when you do laundry, detergents, they contain some sulfonic acid. So detergent, soaps, when you have too much of this from the sewage, they'll find themselves in the lake and the ponds. And if you have too much of these nutrients, it means that the plankton, so the plants in the water, will overgrow. You'll have too much of those plants in water, the planktons. And when you have them in water, of course, the water will not be pure because these plants will compete with the oxygen, with the aquatic creatures in the water. So how does it compete for oxygen? Two ways. One, tumesema when these organisms decompose, decomposition uses oxygen. And then if they are plants, we know that at night, they are going to use oxygen for respiration. So we have that kind of effect. So in many cases, that's what we say. So we have eutrophication. This is just the overgrowth of planktons caused by excess sulfate, nitrates, phosphates in water, leading to suffocation of the organisms which live in water. So I think here we are seeing that when you have fertilizers, they'll cause this. When you have soaps, detergents will also cause this. So these are compounds which are very rich in this. And when you have, if you want to see that this effect has happened in water, then we measure the amount of algae. So you'll see that you'll have a lot of those green stuff, meaning that that you have too much of these substances. And then, so when you have that, I think we have that happening. So again, when you have this, I think there are also some bacteria which will grow and deplete the oxygen demand. When you have those microorganisms, the algae, the bacteria, because they're using oxygen, they'll cause that. And then we talked about the two effects, synergism and antagonism. To antagonize means to act in the opposite direction, reducing the effects. So there are some pollutants, when you mix them together, their effects can be enhanced. When the effect is enhanced, we talk about synergism. When the effects are opposing each other, we talked about antagonism. So they antagonize each other. So I think that's what you wanted to know there. And then we said it's important for us to learn these things as environmental chemists. We need to be able to be involved in this. So we talked about involvement in improving the standard and quality of life. We learned that one here. And also it's important that we do what we call conservation of resources. We need to conserve, especially the forest. We know what they do. If you interfere with the environment, we know that then problems are likely to come in. And then we also talked about how do we conserve this environment. Then we can develop what we call recycling. We can processes where no material is lost. Because again, if it is lost, it means a disposal becomes a problem. And then we also need to come up with techniques that can monitor the pollution. We have another area of chemistry, it's called green chemistry. So green chemistry tries to prevent pollution by using, when you're doing friendly reactions and so on and so forth. But environmental chemistry now looks at the interaction of this, once these products get into the environment, what happens to them? So that's the role of an environmental chemistry. Look at the interaction of these pollutants, their behavior in the atmosphere, And we also try to come up with methods that can be used to determine the same. So there are some government agencies that are involved in checking this ones out. We have NEMA. So they check this one's up. And then there are some rules which have been set to do this. So again, in our review, when we were just starting, we talked about air. And we said what it contains. So good, pure, when you say air, it must contain about 80% nitrogen, 20% oxygen. When you have now the limit passing beyond this, then it becomes a contaminated atmosphere. And then we said for air, it's important because we have nitrogen and oxygen in the air. And this nitrogen and oxygen, normally they are gotten from what we call fractional distillation of air. You can liquefy air, and once you liquefy air, then you can do fractional distillation, where you collect, I think nitrogen comes first because it has a lower boiling point, followed by oxygen. So you can be able to do fractional distillation, then you get that. And in the process, also try to purify the product. You have seen in hospitals where they sell oxygen, so it's normally gotten from the atmosphere. The atmosphere is the source of this. The advantage about this oxygen, it's recyclable. So it's gotten into the atmosphere. Why is the amount constant? Why is the amount of nitrogen constant? The cycle. Inatumika, undergo processes, it forms a carbon dioxide, it reacts to form CO2, and then we have also some processes happening that generates it. Like it is used during respiration and produced during it's used during respiration and produced during other processes. So there's a cycle of this. It will never get exhausted. So it's always generated. So I think we need to note that. And then for the pollutant, just to bring ourselves to speed, the sources, we talked about man-made processes, what we refer to as anthropogenic processes, things like from industries, from our homes, from automobiles, natural processes. These are things like volcanic processes. Those are natural, we have no control over them, but they contribute to pollution of the environment. So then we talked about primary pollution and secondary pollution. For primary pollution, we say they enter directly into the atmosphere. Secondary pollution, the pollutants get into the atmosphere, it reacts with some chemicals in the atmosphere to produce another pollutant. So we have just given an example here. Ozone can react with nitrogen gas. When ozone reacts with nitrogen gas at high temperature, then we have nitrogen, it forms nitrogen monoxide and oxygen. So here, nitrogen monoxide, this one has a direct effect as a pollutant. It's a primary pollutant, but it can react with oxygen to form another pollutant. So a secondary pollutant is a pollutant which is formed from a primary pollutant after some reactions. So natural pollutants, just to say what we had said, they can come from volcanic activities or when you burn a forest. So forest fires, when you burn forests, of course, we know one of the products is carbon dioxide. So you'll be generating a lot of CO2 and you'll also be destroying forest, which is also responsible for absorbing the CO2. So this one causes global warming. Volcanic activity, some of the products produce are sulfur dioxide, carbon dioxide. These are greenhouse gases. No acid rain causing gases. You'll even get nitrogen monoxide, which also causes nitrogen dioxide, which causes which protect part in ozone depletion and also formation of photochemical smog. And then you can also have natural disturbances, which can lead to presence of particles in the atmosphere, solids. So I think this is very common in the US. They have these strong winds, the tornadoes. So these strong winds, when they move, or cyclones, when they move, they carry along with them some particles into the atmosphere, and this can pollute the atmosphere. Okay, so I think this is how we started. So we divided by looking at oxides of carbon. So it's carbon monoxide and carbon dioxide. Oxygen of nitrogen is NO and NO2 mainly. Sulfur oxide, sulfur dioxide, sulfur trioxide. Hydrocarbons, we talked about. Okay, so we have the hydrocarbons, and then the particles. These are the particulate nature. So we have that. Sorry. Oh, somebody is talking. Maybe you can mute your microphone. Joyce Akeka, you have some question?
Yes, sir, please.
Uh-huh.
I need a clarification when you are told to classify pollutants. Are you going to classify as man-made and natural, or are you going to classify as primary and secondary?
It's a broad question. Classification, I think there are 3 types of classification. So one of them is that primary, secondary. You can also talk about man-made and man-made, and the other one is natural. But if they talk about classification of pollution, types of pollution, so for pollution, we talk about water, air, and soil pollution or land pollution. I don't know. So for pollutants, we can classify them into, there are 2 classifications. But for types of pollution processes, then we can talk about the 3 sections which can be affected in the atmosphere. I don't know if I've answered your question. Sorry, I was using when I share the slide, I may not be able to know what's raised his or her hand, but you can just make a shout at it, and then I can pick your attention. Okay, so I think we can continue. We can continue, I think, from there, and then see. Okay. So I think we'll just go back to where we were. We were looking at the notes. Yeah, okay. Oh, what has happened? Just a moment. It's like we have to go back. It's okay. Okay, so I think I don't know if you are here. We'll just get there. Okay, so I think we were talking about these pollutants, the major ones. And then we talked about the effects. So I think here, I remember when we were doing the notes, there were issues here with some arrows, not very clear. So carbon monoxide, we said, this gas is dangerous because it is colorless and non-irritating. So you can just die slowly. You inhale it, it has no taste, it has no color, it has no smell. It doesn't cause any irritation. You just find yourself having difficulty to breathe because of that. And the major source we said is the major source of this we said is incomplete combustion from the engines. And then it is slightly lighter than air, so this makes it even bad because it will float in the air, and that will make us breathe the same. And then insoluble in water, so it cannot be absorbed by water, so it will always come and whatever. So it is poisonous. We have explained why it is. We don't want to focus on that so much. We say it competes with oxygen for hemoglobin. So its affinity is about 320 times that of oxygen. So when oxygen and carbon monoxide, hemoglobin will go for carbon monoxide. And when this one happens, then it becomes a problem. So I think they have just shown the reaction here. HB stands for hemoglobin. It can combine with oxygen to form what we call oxyhemoglobin. But when it reaches the muscles, it can be able to release the oxygen, and then you get your hemoglobin. So the reaction is reversible. For carbon monoxide, the same process also happens. So the same process also happens. So there are observations have been made about this gas, carbon monoxide, in the blood. When it is less than 5% in the blood, then it has no effect. Between 1 to 2%, there are evidence of some behavioral changes. 2 to 5%, it starts to affect the nervous system and impairment, discrimination. And then when it's around 5.0, it causes what we call cardiac arrest, cardiac arrest, or pulmonary functional changes. And then when it is more than 10%, then it causes death, fatigue, headache, and death. So the sources are given just in complete combustion. When you have incomplete combustion of these organic compounds, then you are likely to produce a carbon monoxide. So we saw that it's possible for oxidation to occur by presence of hydroxide ions. So when you have the hydroxide ions, they can just combine, oxidize this, and the products that we get here are in complete combustion of the organic compounds. And then for the oceans, it can come from normally incomplete combustion. So it can come from the algae, it can come from the jellyfish, and when you have incomplete combustion, and then it can diffuse from the ocean to the atmosphere, because tumesema it is not soluble in water. Anthropogenic sources, combustion from coal, combustion from stove, combustion from furnaces. And then the problem that we said, you can, when carbon combines with oxygen, you get carbon monoxide. The carbon monoxide can combine with oxygen to form carbon dioxide. Now the danger here is that the second reaction, where you are consuming carbon monoxide by reacting with oxygen, is a very slow reaction compared to the first one. So it means as you generate carbon monoxide, the rate at which you remove it from the atmosphere will be slower than the rate at which you generate. So what happens in that case? It means it will accumulate, and when it accumulates, that's what we get. Okay, we saw that it's also possible for carbon dioxide also to react with carbon. There's a plus here, sorry. It's carbon dioxide plus carbon, then you get carbon monoxide. So carbon can reduce carbon. We saw this when you're talking about extraction. Extraction, why do we add coke during the extraction of iron? Coke is carbon, because coke at high temperature can combine with carbon dioxide and produce carbon monoxide, which is also a very good reducing agent. So I think you can get that, and then after you have gotten that, then the carbon monoxide, the carbon monoxide is formed, and then under very high temperature, you can have what we call free radical reaction. This one can break down to form carbon monoxide plus carbon. Carbon monoxide, very dangerous. So these are the sources. What we're saying in the notes when you read is that it normally comes from vehicles, vehicles emissions. So it's estimated that for every 7 liters of petrol that is used, you generate about 370 grams of carbon monoxide. And then we know that the concentration is normally high during the peak hours. The peak hours. We also talked about cigarette smoking as being part of that. So we had said that one of the sources of carbon monoxide of this organic product is oxidation of hydrocarbons with the hydrogen peroxide. So here we can see oxidation. And when you do this, you'll start now generating those peroxides, which take part in the photochemical reaction. And then we say when you get these ones, they can also dissociate. And in the process, they form methanol and aldehydes, which plays an important role in that reaction. So I think maybe this section you can just try to read. It's talking about carbon dioxide, what happens to it, and where does it end up. And then to analyze this, we said you can use what we call infrared. We said for gases like CO2, it may not be able to determine that. But for carbon monoxide, because it's a dipolar, carbon is more electronegative than oxygen. It is we normally say it has got what we call dipole moments. Some of us who do physics. So this one can actually be measured by using infrared. So infrared can be used to measure that. So for nitrogen, I think I'll not go word for word again. We are trying to walk through this. So for this, we say so I think for this, we say just note the two, we have given there the 5, but the two common ones are NO and NO2. And now the sources, we say thunder. During thunderstorms, we produce a lot of this in the atmosphere. When that happens, nitrogen in the atmosphere can combine with oxygen to form the NO2 and the NO. And they are also produced in the soil during oxidation. And the product that we normally get is the nitrates. You have heard about leguminous plants, the ones that produce, we convert these compounds into the form that can be absorbed by oxygen. So they can convert them into ammonia, the nitrogenous compounds into ammonia and nitrates, which can be taken by plants. So high temperature combustion can also cause that. So we have the reactions given there. These are things you can be able to read. And then the harmful effects of that, it is stated. So just like C or CO, these nitrogen oxides have also similar effects. At high concentration, they'll also compete for oxygen, for hemoglobin with oxygen. Then we have the fate of nitrogen oxides. So I think this is done. Just those reactions. So this is the section of photochemical. Folk, I gave you better reactions, those 5 reactions that we had. So remember those 5 reactions where it was just playing. So what we need here is the ozone, the hydrocarbon, and the nitrogen oxides. Those are the major components of photochemical smoke. So we have those 5 reactions which you may need to review there. And then okay, and then for the sulfur oxides, we talked about. So I'm just trying to review so that people we can all come to speed. For sulfur dioxide, it is sulfur 4 oxide and sulfur 6 oxide. Those are the pollutants that we should know. And then we also talked about the sources. So we have biogenic sources, or natural sources. They can be formed by decomposition of sulfur-containing compounds, e.g. that by some bacteria, marine algae, and whatever. So we have anthropogenic. So we have biogenic. Biogenic is also a natural source, but it is caused by microorganisms. And then you have anthropogenic. Anthropogenic, these are just caused by human beings through their daily activities, like burning foils, use of sulfur, smelting. Smelting, I think we talked about this when we are talking about extraction of metals. Like copper, we said we get it from copper, iron sulfide. So some of the processes involved in this is to heat it you heat it in presence of oxygen to form copper 1 sulfide, which is heated further to form copper oxide, which you dissolve in, to form copper, which you dissolve in sulfuric acid, and then you clean. And nitrogen for zinc, I remember we talked about zinc blende. Zinc blende is ZS. No, zinc. No, that is zinc blende. Yeah, that is zinc blende. So this one, ZS, when you heat it, it will burn to form zinc oxide and sulfur dioxide. So you can generate this through that. And paper making, we generate it because of when you try to clean the paper. So paper is normally cleaned by use of sulfur trioxide. When sulfur trioxide is reacted with the paper get oxidized. The paper get oxidized, and then the color in the process generates a sulfuric acid. So then we have this one's paper making, burning of domestic refuse will produce that. So fate of sulfur in the atmosphere, we talked about these free radical reactions. So these are reactions when you see atomic elements, it means these are free radical reactions or photochemical reactions, which occur in presence of the UV light from the sun. That's why we have two types. We talk about photochemical and non-photochemical. So for non-photochemical, you'll see the atoms in their normal states, sulfur and oxygen. Here you are seeing atoms, because they are radicals which are formed at high temperatures, and they just break down to form those harmful material. And then analysis of these compounds. So we said we can do what we call qualitative analysis. Qualitative analysis tells us what you have. Quantitative analysis tells you how much you have. So for these compounds, to analyze them, we normally use what we call a UV machine. So a UV measures the concentration of these compounds in form of colored compounds. And that's why to measure this, you normally prepare the sample to produce color forming compounds. And then the color forming compounds are analyzed using UV to get the colors. And then I think the effects, we talked about the effect of sulfur dioxide. So ukiona sulfur dioxide, just think about acid rain. How does it affect human beings? How does it cause? It destroys the plant. When you have excess acid, it interferes with the formation of chlorophyll, leading to poor crop yield. For non-living organisms like materials, of course, the effect is corrosion. And then when you have sulfate particles, then visibility becomes a problem. We have talked about acid rain. The pH of rainwater will not be neutral, but it will be acidic. And then on food, so for the forest, we said causes leaching. When you have this acid rain, it will dissolve most of these metals, and they'll be able to flow in the water, bedrocks, and be absorbed by the plants. Aluminium, too much acid will favor the uptake of aluminium. And I remember in one of our classes, we said aluminium is not good for plant growth. And then talked about the effect on fish, effect of drinking water. When you take this one, it irritates the gas pipe, corrodes the gas pipe, can even causes cancer. So what we do to take care of the acid rain, I remember we said we can use lime. We normally add lime. One of the causes of acidity in water, in the soil, is because of use of these inorganic fertilizers. So they're very acidic. When you add them, they make the soil acidic. So to take care of the acidity of the soil, we use calcium hydroxide or lime to react with the acid. Like here, if it is calcium, if it's sulfuric acid, the calcium hydroxide will react with sulfuric acid to form calcium sulfate plus water. And then we also talk about, so liming is done just to reduce the acidity. So when you have this acid rain, it can also corrode pipes. Previously water used to be made, pipes used to be made, plumbers used to use lead pipes to fix the water system, but slowly it's being replaced by plastic, because if the water is acidic, it was dissolving this lead, and the lead was finding itself into our bodies. And I think we talked about the effect of that one, the lead. Then we have physical chemical methods of determining that. I think there are different methods that can be used. So to control, I think, sorry, I'm jumping around here. To control sulfur, we said we use petrols which don't contain sulfur, so you control the amount. The process is called resulfurization technique. So the process so we just try to control. We use techniques that can be used to remove sulfur from the soil. So I think a number of these methods have been given. And then we also say there are some bacteria that can actually break down compounds containing sulfur and form other compounds. Okay, so I think for the particulate matter, we talked about the particles, mostly the organic compounds. They interfere with visibility. They can also cause odor or smell. Okay, so for the hydrocarbons, and then we talked about this reaction. So photochemical, when we talk about photochemical reaction, this is reactions which involves the free radicals at very high temperature. So I think there's a better note that we used to explain this, how they are formed. And then we said normally we could have a third body which acts as a catalyst and is given the symbol M, a third body that helps in the reaction. So remember we talked during the photochemical smoke, we said ozone can break down to form oxygen gas plus oxygen atom. The atom can combine with water to form the water radical. So the water radical that is formed, we said, is important in oxidation. So you can see in the second reaction here, the OH is oxidized with carbon dioxide to give carbon dioxide plus a hydrogen radical. And the same OH can also react with nitric oxide to form nitric acid, which causes acid rain. The same OH can react with sulfur dioxide to form hydrogen, to form I think there is some typo. That one is supposed to be sulfur trioxide. There is no -3. So the -3 is not there. So this -3 is not there. So it is just sulfur, I know this compound, which is a free radical, hydrogen sulfide. And then this hydrogen sulfide, when you react with OH, it gives you that. So there's an arrow between this. So it's this compound plus OH to give you that. And then this one just shows further oxidation of these compounds. And just remember the atmosphere, we were talking about the various parts, the troposphere, stratosphere, mesosphere. Know what is there and what takes place within that. So I think I'll not want to go word for word. We talked about photochemical smoke. Don't forget this and the reactions, the 5 important reactions. Maybe I think we can review up to there. So for the particulate, we talked about that. Maybe we can review next from chapter 6, but we can, I wanted us maybe to look at the end of the notes, towards the end, and then we can start reviewing. There are some parts. So we can do chapter 6 and 7 just to review. Next time, there are things which are not here, we may need to. So we can do 6, 7 in our next class before we introduce the next one. Okay, so I think these ones are related to what we had said before. You can be able to look at them and see. So these ones, detergents, what are they? Okay, so I think we'll review these ones Just allow me 2 minutes. I upload something and then I come back to you. Just a minute. I just upload something. Let me see. MKU. Just a moment. Just a moment. There's something. Compose. Desktop. Yeah, sorry for that dead moment. It's okay. 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 Here. Okay, maybe you can take a few minutes just to look at some. I think there is a section of the notes which talks about extraction of non-metals. We had looked at extraction of metals. So for the non-metals, we talked about sorry, sulfuric acid through contact process, ammonia through Haber process. The other non-metal that is normally produced in large amount is chlorine. And I just remember in class we talked about extracting it using electrolysis of brine. Brine is just a concentrated solution of sodium chloride. When you do electrolysis of this, then you'll see that we produce chlorine gas and hydrogen gas. So we produce those two gases. So this notes, which I think you have, I think it's talking about extraction of chlorine. I sent you as a zip. It's normally done from electrolysis. Electrolysis means you pass current through a compound and the compound breaks down to produce ions, and these ions move to different electrodes depending on their charges. So when you have a solution containing concentrated sodium hydroxide solution, this solution will contain water, and water has what we call hydrogen ions plus hydroxide ions. So the negative ions, hydroxide, no, the negative ions, hydroxide, the positive ion, hydrogen. From sodium chloride, which is the brine, the positive ion is sodium, and the negative ion is chloride. So you have, so when you do electrolysis of this solution, the positive ions, which is hydrogen and chlorine, will go to, no, the positive ions, which is sodium and hydrogen, will go to the cathode. And the negative ions, which are chloride ions and OH ions, will go to the anode. Now at the anode, no, at the cathode where you have hydrogen ion plus sodium ion, a number of things are likely to happen. So what you'll have happening there is that if you are using carbon electrodes, then hydrogen will gain 2 electrons to form hydrogen atoms, which will combine to form hydrogen gas. At the anode, when you have OH and chloride ions will be discharged because of high concentration. The solution is highly concentrated. So chloride ions will go to the anode where they'll be oxidized. So anode is oxidation. Negative ions go there to get oxidized. At the cathode, positive ions go there to get reduced. So cathode means cation goes there. Anode means anion go there to get oxidized. So the anion will be chlorine, and then so you just generate it by electrolysis. So when you look at the overall reaction here, we are saying that if you have sodium chloride, during your electrolysis, what will end up forming is chlorine plus hydrogen. And then what happens is that now the sodium which were left behind, the sodium which didn't take part in the reaction, will combine with the OH from water to form sodium hydroxide. So the product here that you get is sodium chloride plus water. No, the product that you get here from brine, which is concentrated solution of sodium chloride plus water, is chlorine, hydrogen, and sodium hydroxide. If you are to use potassium chloride instead of sodium chloride, the product will now be chlorine, hydrogen, and potassium hydroxide. So I think this is done through electrolysis. There is a figure here which shows that the cell is divided into two. So we have the same cell. So this diagram just shows the cell and how it works. So what happens in this cell is that it is divided into two chambers. So there are two chambers. So you have the chamber now separates the anode from the cathode. So there is the negative electrode, which is the anode on the right, the positive electrode, which is the cathode. No, the anode, sorry, let me just repeat that one. So the chamber is divided into two. On the left, we have the negative electrode, which we call cathode. On the right, you have the positive electrode, which is called the anode. At the anode, this is where we have oxidation happening. Now, this cell is divided by a semi-permeable membrane, or a membrane that can allow cations to move through. So cations are allowed to move through an ion exchanger. So it can allow that to happen. So when you put your solution, so what happens is that in this chamber, we introduce sodium chloride, and we also introduce water. So in the inlet, what you put in the inlet are sodium chloride plus water. And we have just said from our reaction up there is that at the anode, what will happen is that chloride ions and hydroxide ions will move there. So the anode will have chloride plus hydroxide. But we said hydroxide ions, because they are less concentrated, what will be discharged there from that solution will be the chlorine. So chlorine will be removed, will be evolved at the anode. At the cathode, we have said we have hydrogen ions and sodium ions. So what will happen is the sodium ions will be reduced to hydrogen atoms, which will combine to form hydrogen gas. And then the sodium, remember we said the sodium ions which were in solution will now combine with the hydroxide, which remained, and they will be released as sodium hydroxide. Now what you are seeing here is that the solution which is coming out is less concentrated. So you put in a more concentrated solution, you get out a less concentrated solution. The reason for this is because during the process, we are removing the chloride ion, so the concentration of the solution formed will be less. So this is the technique that we normally use to extract chlorine. And we need to know why chlorine. Why do we produce chlorine in large amount? Remember, we said chlorine is used as a disinfectant to clean water. Chlorine is also used as an oxidizing agent. When you talk about sodium hypochlorous and other forms, we can get it from this end. So this is how we extract a chlorine as a gas. So chlorine as a gas is extracted through electrolysis of brine, which is just sodium chloride concentrated. And then there is this part, I think, which we had done. We had done this when you're talking about how do we extract nitrogen and oxygen from the atmosphere. So we said it is through electrolysis. It's through electrolysis. And then for hydrogen, so hydrogen is just gotten from natural gas. I think we have heard about. So I think this one is just fractional distillation of liquid air. It's called cryogenic distillation. Cryogenic is they normally call it a boiling liquid. When you cool gas and then it condenses to form the liquid will behave as if it is boiling. So they are called cryogenic liquids. So you cool to form liquid and then you separate using fractional distillation, where you separate them based on the temperatures. So I think that's what we are trying to run through here. So based on the temperature, you can be able to separate the gases. You cool, get a liquid, and then you heat the liquid and collect the fractions at different temperatures. But before you do that, again, you have to clean the gas by removing things like water, removing things like carbon dioxide. How do we remove carbon dioxide? We remove carbon dioxide by passing the gas through sodium hydroxide, which will absorb the carbon dioxide. So, or sometimes you can use what we call molecular sieves, which are able to separate some molecules and leave others. So this one, I think after you have done that, you'll just do fractional distillation and then you get the product. So we said the applications of nitrogen, it is in the formation of ammonia, which is a very important product. And then liquid nitrogen, we said is also used because of its inertness to preserve food and even store biological samples. It is also used when you want to carry out reactions under inert conditions. They can be carried out in a chamber of nitrogen. And sometimes it's also used to preserve metals. So metals sometimes are stored under liquid nitrogen to prevent them from undergoing oxidation. Now there's also an important gas. Nitrogen is also an important gas. There are developing countries, some developed countries have already come up with vehicles that uses hydrogen as a fuel. The advantage of using hydrogen as a fuel is that when it's oxidized, you get water, and water is a friendly product, not like carbon dioxide. So that's so it's normally formed from what we call a natural gas, or sometimes it is referred to as steam methane reforming. So it is formed from methane. Methane is just CH4. So what happens is that this methane is reacted with steam. Steam is water at very high temperatures. And then, so when they combine, I think the reaction is given here. The methane combines with steam to form carbon monoxide plus a hydrogen gas. So you can be able to generate your gas. And then carbon monoxide can also combine with water to form hydrogen gas. So this is one of the methods of forming hydrogen. So it's just react hydrogen with water. Now react hydrocarbon with water at high temperature, it will form that. The other method of forming hydrogen, it can be formed by partial oxidation of hydrocarbon. So this reaction has been found to occur where we refer to it as thermal partial oxidation of oxygen, where the gas is partially oxidized to form CO2, to form CO. So just partial oxidation means oxidation does not go to completion. So there are some reactions which are given here. So like this compound, when you oxidize, you get carbon monoxide and hydrogen. So partial oxidation. And then there are some reactions which are done by use of electrolysis. You can split water. Splitting of water just means breaking it to form hydrogen and oxygen, but it's a very expensive process. So I just wanted to rush through those processes. Production of hydrogen, we can do it by steam reforming, where we react hydrocarbon with water to form carbon monoxide plus oxygen. You can do partial oxidation, or sometimes you can do what we call water splitting, where you split it to form hydrogen and water. I may wish maybe to stop there for now, so that we give ourselves time to digest that. So I think for those who came early, we said we have agreed we extend the CAT deadline submission to tomorrow, 8 p.m. And we'll just request those ones who send their CAT via email kindly kindly download and then upload. So we're giving them up to tomorrow. tomorrow to submit. So I think so that we don't have people complaining.
Hello, doctor.
Yes.
Professor. Hello, professor.
Yes.
Just asking.
Yes.
Because I submitted my assignment through the portal. But today I've tried to locate in the assignment, but it says it's no longer there. I don't know what happened.
You tried at what time?
I hope it was around 3 today. That is around 30 minutes ago.
Yeah, you don't know what. Maybe I'll check. Let me see if I can.
I hope you have downloaded.
Mine has the same problem also, so I don't know what's the problem.
Or are we supposed to resubmit?
Let me e-learning.
Yes.
I can just check on e-learning MKU.
Okay.
Let me just check and then I tell you.
Okay.
Right, login required MKU e-learning DBEL. DBEL virtual. 46. So click the course, I click assignment. Okay. Let's see. Okay. So what I'm seeing the assignments here.
Yes.
For what's your name?
My name is Willie Kipchumba. Yeah.
Let me see if I can see it, Kipchumba.
But I saved
Kipchumba,
using Kipchumba, Willie Kipchumba. That is PETS 56873.
Willie Kipchumba, I know it's there. I can see it. It's there.
Oh, but in my site, it's not there. If you have it, there's no problem.
Willie Kipchumba, I think I have it.
Okay, thank you.
You can see Willie
Kindly
Kipchumba.
check mine also because I don't know my face.
What is your name?
I was just requesting for these notes you are using at the moment because it seems I don't have.
I sent it to Dennis. Dennis, you didn't give the second one. There was a folder. I sent a zip file. Maybe Dennis can forward to the class.
Okay, thank you. Maybe
okay, kindly check mine.
Okay, what's your name?
My name is Eda Chebitok.
Eda
Chebitok, PEDS 2022-56-813.
No, the name is
Eda Chebitok.
Eda.
Yes.
Eda Chebitok. Eda Chebitok. Eda Iko.
Thank you.
Something 2022-56-813, eh?
Yes, that one.
Iko.
Okay, thank you.
Iko. I think I'm just happy that we are moving on well. Kuna wengine tukiweka class wanasema wako na class ingine, tukiweka hata time ingine they fix another class. Sasa inasumbua to move on, but I was thinking, I think so that we make progress, we shall continue to meet. I'm told you are starting exams on the 14th, eh?
Yes.
Okay, so I think next week we have time to clean up. So can we meet, when can we meet, Monday or tomorrow?
Tomorrow evening from 7.
Okay. Is it okay with the other people? Tomorrow we can rest and then we meet on Monday. What is the opinion of the class?
For me, I propose Monday.
Wacha kesho tupumzike kidogo. Just try to catch up with what we have said.
At what time?
Monday, can we say 4?
Yeah.
Bado mtakuwa shuleni.
4. I hope it is possible. Maybe we can hear from the rest of the class.
Badala ya kutana usiku Monday, we can even make it from maybe 3 to maybe 4 to 5:30.
Wengine hapo tumefunga, hatujafunga shule bado. So kindly maybe from 5. 4 bado tuko shuleni.
Shuleni sawa. So what about that proposal? Can we do it from 5 to 6:30? We can still go back to 7. I've no issue. Kama wengine wanaona wafike nyumbani kwanza, they settle kidogo.
Kama unaona ngumu, tunaweza fanya from 6.
Bora watu wapatikane. Saying is easy.
Yeah, 6 p.m.
I know some of us are mothers, sasa pengine wafike wajipange kidogo.
So or we can share through the WhatsApp. Yeah, from 6 or 5.
From?
Either 6 or 5 p.m. Monday.
Okay.
Yeah.
Okay, Paul, I think what messed us up is we started late. Maybe if we'll be having classes with you guys in future, we'll start in time and then we'll be more organized. So I think the contribution of the disorganization has been starting late. But but I think we'll be able to do that. The beauty about this course, it is a bit general. It's not like the physical chem one, where you need to go through those equations and develop them from the first principle. So maybe that's the advantage that we are hanging on for now, is that it requires a bit of, the chemistry is not very, very deep. But if it's a physical chem course, then it was going to become very unfriendly, because it needs you develop the concept slowly. But I think we were forced to rush at some point because of that. So I think I would wish we stop there. I think today has been very productive, I believe. And I think as we do this, we'll get to know most of this. So when we meet on Monday, you can review the last 2 chapters and then we bring in something else. But I'm very happy. I think it's okay. Edna, you wanted to say something? I can see your hand. You have raised your hand.
It was about the cards.
Okay.
As you already helped me, thank you.
Okay, thank you. We'll do it. I'm not bragging, but I'm not a bad lecturer. It's just that we started late. But I think if we'll be doing some courses together, you'll appreciate. I'll be able to do a better job. But I think let's try to see how best we can get out of the situation. And I thank you very much for sacrificing your weekend just to make sure that we move on together. Thank you. I appreciate. And you have a nice weekend. And God bless you. Thank you.
Thank you too, Prof.
Thank you, guys. Thank you for sparing your time. At least we can move on. Thank you. So let's stop there. And God bless you.
God bless you too.
Brown. Hello, Brown.
Yes.
Brown, nimetoka tu kidogo class nikarudi wakiongelea cat.